Hi dear students, good morning. So let us look at the estimation of critical constants. Okay, we know what are critical constants. If we look at the previous first section where we looked at the using Andrew's experiment, what did we notice is critical constant, that is the temperature at temperature 31.1. It was found that for carbon dioxide gas, it was found that uh, what is happening at this point. So above this point, above this critical temperature, the gas obeys Boyle's law, while below that it first it obeys Boyle's law, and then it is changing its phase from a gaseous to a liquid state, and then it remains in a liquid state just on application of pressure alone. Okay, this was pressure versus volume. Just an application of pressure, this is what has happened. So now let us determine what is this value, that is what is the equation for to determine what is the pressure, critical pressure, what is the value to determine what is Vc, that is this value, as well as Tc. Okay, so we're going to determine that and how we do that. So let us consider this critical isotherm ACB, okay, as shown in the figure, where T is equals to Tc. Now at this critical point, the curve is slightly horizontal at point C. Okay, so when that happens, if you want to determine what is the derivative with respect to its volume, we will get it as 0. And since, see, it's a horizontal, it doesn't have a peak, or it doesn't have doesn't have a trough, so it's neither it doesn't have a maxima nor a minima, since it's a horizontal line. So since it does not correspond to either a maxima or a minima, the double derivative of pressure with respect to volume will also be 0. Always at a critical point, whenever we talk about a critical, always at a critical point, just remember these two things: this first order derivative dp with respect to dv, dp with respect to volume, and the second order derivative d2 square with respect to dv square is equals to 0. Now let us look at my van der Waals equation of state. What is a van der Waals equation of state? P plus A upon V square into V minus P is equals to RT. Now what have we done here? I have kept P on one side. So what I do is I keep P plus A upon V square and is equals to RT. I can take this V minus P down, correct? That is what I did. Then the next step, I keep P on one side, I take A upon V square on the right hand side, so I get a negative sign. So now what I'm going to use this equation, say I name this equation star. I'm going to use this equation to determine one thing, dp by dv, to find out what is the derivative of this, but I also know the derivative of this will be equated to 0. Similarly, I'm going to determine what is the second order derivative. Now how I do that? Okay, let's look at this equation star p. Now to determine what is the first order derivative of this, how can I write this equation? Can I write this equation like this? Okay, so what I do is, now I want to find dp by dv. So can I write this as RT into, can I write V minus B raised to power of minus 1? Okay, and on this side, can I write it as A? Instead of V square, can I write it as V raised to power of minus 2? I just taken it all in the numerator. So I've taken this equation like this and written it. Now if I want to determine what is the derivative of this particular equation with respect to volume, what do? I can write it as, so first RT, there is no volume term here, but there is a volume term here. So I look at the bracket, I look at the terms inside the bracket, and I look at the bracket as a whole. So first I can write RT as it is. Okay, now minus 1, it's like derivative of this bracket raised to power of minus 1. So it is like a raised to or x raised to power of n. Derivative of x raised to n is given as n into x raised to n minus 1, right? So here what is my n? Here my n is minus 1, correct? What is my x? My x is my entire bracket. So v minus b, 1 minus 1 will give you how much? Minus 2, correct? So that's how I get minus RT. So what I get here, I'm only looking at this equation, okay? This is what I get. I write minus RT, so this minus 1, I write minus RT, and I write V minus B raised to power of minus 2. This can further be written as minus RT divided by V minus B the whole square. Is this understood? Now let us look at the second term, minus a upon v square. So minus a into v raised to minus 2. So what can I write this as, since it's so minus 2 into minus a can be written as plus 2, right? Same thing, it's derivative of v raised to n. So minus 2 into this will be plus 2a v raised to power of minus 2 minus 1. So I get minus 3. So I can write this as 2a upon v raised to 3, correct? That's how I get my term. I get minus RT plus 2a upon v raised to 3. Clear? How I get dp upon dv? Let us look at the double derivative now. Okay, double derivative. Yes, now it's all clean and clear. Moving on to, let me look at this. Okay, now I need to find what is the derivative further on of this entire thing. So what I get is, I look at this first term, minus RT upon V minus, so I have minus RT. I can write this V minus B, which is in the denominator. I can write it as minus 2, okay, plus I write 2a into v3 cube is in the denominator, so I write it as minus 3. So to find a derivative of this, again I look at only the bracketed term, since I'm finding with respect to volume. So again it's like x raised to power of n. What is my n? Minus 2. Derivative of x raised to power of n is n into derivative is n x into n x raised to n minus 1. So what I get is minus RT. Now what is my n? My n is minus 2. This is minus 2 into v minus b raised to power of minus 2 minus 1. Okay, similarly I write plus, I look at my 2a, there is no v term since it's this, so here again it's x raised to power of n, so minus 3 into v raised to minus 3 minus 1. So what I get is minus 2 into RT. Can I write it as 2RT? 2RT plus, correct? And this, I can take this in the denominator and write it as V minus P. So minus 2 minus 1 will give you minus 3. If I take it back in the denominator, I can write it as 3. Now here 2 into 3 is 6. Since I have a minus sign, I have minus 6a divided by v raised to power of minus 4. So I can write it as v raised to 4. So this is how I get my double derivative. Alright, now let us determine what are the values, or how can I find out what are my critical constants. So considering that critical isotherm that we see ACB, okay, with its critical point at C, since the C is the critical point, it resembles something known as a saddle point. Saddle point is a point which has neither a minima nor a maxima. Okay, since if you look at the curve, it's something like this, and this is my critical point. So it's a horizontal line. So it doesn't have a maxima nor a minima. And at this particular point, we know that the derivative with respect to v is equals to 0, and the double derivative d2p by dv square is equals to 0. That is now what we have found out. So what we can do is equate these two equations to 0. Now point C is also called as a point of inflection. So what we say is, therefore we say the tangent, okay, that is drawn at such a point is said to be stationary, and that point is said to be called as a point of inflection. And the point of inflection is, we add the point of inflection, we have the derivative d2p by dv square is equals to 0. Okay, now my van der Waals equation of state. So we have this as equation 1, correct? We have this as equation 2, what we found out, and equation 3. But now at point C, we know that T will become Tc. So wherever there is T in these three equations 1, 2, 3, it will be Tc. Wherever there is P, you will write it as Pc. So this will be Pc. Wherever there is V, will become Vc. And these equations, so this can be equated to 0, and this also can be equated to 0. So let us, using equation 1, 2 and 3, let us look at the first equation. So wherever there is P becomes Pc, T becomes Tc, V becomes Vc, again V becomes Vc. Okay, this is from equation 1. Now from equation 2, we know that this is equals to 0. So we can write that the right hand side is also equals to 0. And on doing that, so from equation 2 we get this. Okay, then we just rearrange the terms. We take RTC on the other side upon VC minus B the whole square on the side, and keep 2A upon VQ on this side, thereby giving us equation 5. Similarly, now from equation 3, okay, from equation 3 we get this equation down here. We just rearrange the terms and we get this. Now we take equation 5 and equation 6. Now let us look at this. So from equation 3, what have we done? We have taken this and we have equated to 0, and then we have kept 2RT on one side and this term on the other side. But mind it, we have changed T to its critical value, that is Tc, V to its critical value Vc, and P to its critical value Pc. So we get equation number 4, 5 and 6. Now let us divide equation 5 by equation 6. So what we do? We take the left hand side first. We take RTC, so we'll get RTC upon Vc minus P the whole square. I take this and I take this, and now I have to divide it by this term. What I do there is, so I will get 2RTC divided by Vc minus P the whole cube. this is of the form a upon b upon c upon d. So it can be written as a upon b into d upon c. That is what is done here. So we have taken a upon b into d upon c. Similarly on the right hand side, a upon b into d upon c. So this is a upon b, this is like my a, this is like my b, this is like my c, this is like my d. A upon b into d upon c. So vc minus v the whole cube upon 2 rtc. Similarly 2a upon vc square into vc raised to 4 upon 6a. After doing this can cancel. We are left with vc. A goes off. We are left with 2 upon 3. So we are left with vc upon 3 on the right hand side. On the left hand side, this gets cancelled. I'm left with one term on top, vc minus p, correct? RTC goes off, divided by 2. So I get this equation, vc minus p upon 2 equals to vc upon 3. Now we have done all this only to determine what are the critical constants. And in what form we get them, let's look at that. So now what I get is, I get vc minus p. So let's look at this again. So I can write this as 3 times vc minus p, okay, equals to 2 times vc. Then what I get 3 vc minus 3b is equals to 2 times vc. So what I can do is, I can bring vc terms on one side. So 3 vc minus 2 vc. I can take my 3b term on the other side. So I get vc is equals to 3b. So I got my value of my first critical constant, or the expression for my first critical constant, that is of volume, and I have got it as vc is equals to 3b. Now what I do is, I substitute equation number 7 in equation number 5. So wherever there is vc, I will write it as 3b. When I do that, I will get my value of tc, right? So what I do is, this is my equation number 5. So wherever there is vc, I substitute it as 3b, 3b, 3b over here. So 3 3s are 27, 3 3s are 9, 9 3s are 27. So I get 27b cube upon here 3b. Now what I do, 3b minus b will give you 2b. So 2a. Now I'm rearranging these terms, okay. So what I get is, I keep, so I have my RTC is equals to 2a into 2b the whole square, correct, divided by 27b cube. First of all, what I can write this as, 2 2s are 4, so 4 2s are 8. I get 8a, correct, b square divided by 27b cube. I can cancel, this gets off. So I get 8a upon 27b, and since I want tc on one side, I can bring this r in the denominator, therefore giving me my value of my critical temperature, that is tc is equals to 8a upon 27 br. Okay, now what I do is, I substitute for tc, take tc, and I take my vc, what I've got. So I take the value of vc, I take the expression for tc, and I substitute in my equation number 4, since I have to determine what is pc. If you notice, since I've gone step by step, determine what is vc, then I've gone determine what is tc, now pc. So I substitute. This is my equation number 4, okay. Now wherever there is tc, I substitute it as 8a upon 27 br, and wherever there is vc, I have substituted as 3b. Similarly 3b, so 3b square, 3 3s are 9, 9b square I got. Now here what I get pc is equals to, now how do I get this, 4a upon 27b. So what is done here is, R, alright, upon 2B into 8A upon, so this is what I can get, this is 2, this will get cancelled, so I get 4A. So okay, instead of doing this step, let me look at it as R, okay, 8A and 2B will come, right? So I get 4A divided by, okay, this R can also get cancelled, so I can erase this R, so I get 4A, okay, 2B upon, what will remain here is B, and there is 27, so I have 27B square minus, I get A on the other side, correct, upon 9B square. Now what I do is, I want to keep this as denominator as 27B square, so I take the LCM, so I get 4A 27B square. To make this 27, what do I have to do? I have to multiply and divide by 3. So I multiply my numerator by 3, and 3 into 9 will give me 27. This and this means the same. Actually, if I cancel this, I'll get again A upon 9B square. Just to equate the denominator. So 4A minus 3A will give me A divided by 27B square. So here I have got my value of my PC as well, which is my critical pressure. So if you notice, all these critical values, they are dependent on van der Waals constants. And if van der Waals constant change for different gases, likewise even the critical constants will vary for various gases, correct? So we'll do this next part later, that's the expression of van der Waals constants. But before that, this is what we have done today: TC, VC and PC. Alright, so kindly go through this. If you have not understood any step, please let me know. Okay, so the critical temperature and pressure varies for various gases. Okay, some will be in steps of maybe in the minus degrees, some will be in positive. Anyways, we won't get into what are the values. Just look at this. So PC is A upon 27B square, TC is 8A upon 27BR, and VC is 3B. So equation number 7, 8 and 9. Please keep in mind these equations, or you can even derive it for your problems. Okay, thank you, have a nice day.